Morning, everyone. So I wanted to overview some of the main concepts that we hit in this solubility unit here. Hopefully it will be useful for highlighting some of the main themes and going over some practice questions. So remember in this section here, we were mainly looking at solutions. Although when we make solutions here, we can dissolve, let's say, gases into liquids. We focus primarily on dissolving solids into liquids, forming aqueous solutions here. So a solution here, just a reminder, it is a homogeneous mixture. It's a mixture because the chemicals themselves are not necessarily attached to each other. Ions would have been dissociated, but they are homogeneous because it feels like one material. It feels like it's all in one phase. It's a homogeneous mixture made by dissolving the solute, which is again the thing that's in lesser quantity, into solvent. For the solvent, it is the thing that's in greater quantity, and we're going to always assume that the background is water, although in chemistry you can dissolve in any type of liquid. You can dissolve it in hexane, you can dissolve it in petroleum ether, right? And your solubility will actually depend on what the solvent actually is. So pictorially here, we're saying we have our beaker, it's filled with water, you have your solute. As long as your solute is outside the water, it can stay in the solid state. So for example, let's say this is table salt here. Although our solubility chart here would say NaCl here is a soluble salt. Soluble means it dissolves very well. Usually we would say, okay, it dissolves very well, aqueous. Well, why am I allowed to put NaCl here as solid? Well, it's only aqueous when it actually is dropped into water. So perfectly fine, NaCl, it's ionic, it's a lattice here, ionic bonds keep that structure here, so very, very hard to melt. Solid state is no problem. It's upon tossing in water, pretty much because it's so soluble, the NaCl here dissolves, no problem. You can keep dissolving this in here. Because the sun here is very soluble, it's going to take a ton before you hit saturation. You're going to eventually hit a point where when you toss some more salt, sure, a lot of it has already been dissolved, it's really, really salty water, and now when you toss in more solid, that NaCl seemingly just sits there, right? At the point where the solid first occurs, we're going to refer to this solution as having become saturated. So a saturated solution, that word saturated means it's completely packed full. In this case here, a saturated solution, it contains the max amount of dissolved solid. Remember, the liquid is water here. There's sort of spaces left behind as the particles in the liquid slip and slide past each other here. There's some limit to how much NaCl it can actually dissolve in. Something that's very soluble, you can dissolve a ton before this happens. Something that's less soluble, let's take silver chloride as an example. Silver chloride, again, outside of solution, it can be solid, no problem. But silver chloride on our table, it's referred to as either low soluble or even insoluble, which refers to the fact that this one here dissolves very poorly. So upon dropping in water, it typically remains a solid. Everything will dissolve to a certain degree, so you might add a smidgen of silver chloride, you might manage to dissociate a little bit of it. That's when the ion concentrations are not high enough to actually hit saturation. But being a low soluble compound, it doesn't take much more than that, and it's already solidified out. So both soluble things and insoluble things here can hit saturation. It's just a matter of how much until that occurs. Remember, there's a totally arbitrary limit here. On our solubility chart here, we define the word soluble as having dissolved more than 0.1 mole per liter at 25 degrees. Right? It didn't have to be 0.1, but that's just what we referenced. So if you check out your chart here, you can check it compound by compound. You check out the negative first, you counterbalance it with the positive, and you look at the matchups, and you see on the right-hand side, is something soluble? Will it dissolve more than 0.1 molar? Or if it's low soluble, it doesn't. You always have your solubility chart with you, but there's some nice memory aids for you here. We found there are some things that are always soluble with any negative compounds, and those ones here in terms of the positive, if you have any alkali salts, so group 1 ions, lithium, sodium, potassium, if you have any H plus salts, if you have any ammonium salts, those are always soluble. And in contrast here, if I want to put in any particular positive ion, and I want to figure out, well, which ones are guaranteed to be soluble for the negative, nitrates are always soluble. So that's just a nice memory aid for you here. These salts here are always soluble, so you don't even need to bother checking these ones here. They're going to dissolve really, really well. Whenever we're doing dissociation, we're going to assume that we're really, really far away from the saturation point. In a lot of this chapter here, we were focusing not just on the solutions themselves. We dealt with concentration problems last year. We wanted to emphasize more so this notion of saturated. So you notice that in this picture here, in a saturated solution, definitely you have to have undissolved material present. Right? It's completely packed full. Any excess that I drop in is just going to sit around. The reason why we need undissolved material present is when we use the terminology saturated, we actually refer to the system has reached dynamic equilibrium. What is the equilibrium between here? The equilibrium is between the rate of dissolving. Right? That's why we need solids still present here. So this particle, although macroscopically it looks like nothing's happening, it is constantly dissolving. It is constantly dissociating and breaking out. That's called dissolving. But we matched up the forward rate is equal to the reverse rate. The ions themselves in solution are also jumping back out in the reaction called recrystallization, rate of recrystallizing. Again, I'm going to remind you here, at equilibrium, we have the fact macroscopic properties. So outwardly, it looks like nothing is changing. Macroscopic properties are constant in time. Right. Sometimes it's a little bit misleading when you look at a cup of salt water. Let's say I've completely saturated it. We have undissolved material present. The salt is so fully dissolved into the homogeneous mixture, it doesn't look salty at all. You can't just skim off the top and be like, oh, that part's clear, that part's not salty. In fact, by the time you have a saturated solution, especially for something that's really soluble, it's actually at this point here where it's actually, there's the highest concentration of salt. It's going to be really salty water even if you skim off the solid at that point. Microscopically, reactions continue to occur. Microscopic reactions continue to occur. So if I could tag these molecules here, tag the solids that I actually drop in, these particles here in time, they are going to jump into solution. But overall, I don't see any change because there's other things that are coming out of solution at exactly the same rate. So there is a certain sweet spot where I'm basically going to do this experiment. I'm going to start off with just pure water. I'm going to slowly drop it in, and I'm going to find sort of, that, as I mentioned, that first instance when it becomes saturated. We're going to give that a name here called solubility. So solubility, another term that we definitely want to know. So solubility describes the maximum amount of solute that can dissolve. Usually they specify the same terminology here to form a saturated solution. Again, the whole notion here is you've just maxed it out. You just have undissolved material present. We wait a little while for an equilibrium to be established, but that represents the maximum. Any extra that I add in, sure, you can toss in more solid. The amount of solid, the amount of material there is greater, but since I've already hit the solubility limit, no more of that would dissolve into the liquid. The concentration at that point there is sort of fixed. For this solubility here, first type of question in this setup here is they're going to ask you, well, depending on what I'm actually tossing in, is the solution going to be referred to as an electrolyte or a molecular solution? So all that classification here is it's just separating. We have ionic compounds as separate from covalent compounds. Ionic compounds are referred to as electrolytes. So electrically conducting solution, covalent compounds will end up forming molecular solutions. How do you recognize something to be covalent? Typically, the organic examples will be covalent. So organic compounds are based off of carbon. It's usually going to be C something. So if I just gave you a quick list here and I said, okay, we have NaCl, we have C3HCl, we have MgCl2, and we have CH3COH, right? They can ask this question a couple different ways. They can say which of these solids here, which forms a molecular solution. That word molecular just implies not conductive. It's a solution where the chemicals I'm dissolving are just remaining as molecules. The things that remain as molecules are actually covalent compounds. So I'm looking for a sort of non-metal kind of connection here. Usually it's going to be carbon with something. So I'd recognize this one here should be organic. This Jaku here is also going to be organic here, but we'll talk about that in a second here. This one here is a covalent compound. So when you bubble this chloromethane here into water, because this is covalently bonded, the CH3Cl actually doesn't break up in solution. These covalent bonds are a little bit too strong. So when you bubble this into solution, it's going to remain as molecules of CH3Cl. Sure, you can trap a little bit of it inside. It's been aqueous, it's dissolved and whatnot, but water cannot actually break in these covalent bonds because the covalent bonds are actually strong. So in that case there, we have a solution that's molecular. We have no charges, and the charges, well, there's no charges that are moving around, so definitely not conductive. So if I have a covalent compound, we typically say it's non-conductive. Ionic compounds in contrast here, I can ask you sort of following up here, I can say which of these solids, okay, which salt forms the most conductive solution. All right. So first thing they ask here is, okay, I want to know which ones are conductive. We've been saying already, the conductive ones, I need to check that I have charges. Ionic compounds will always dissociate to form ions, so that's where my charges are going to come from, but these charges here have to be mobile. So for example, let's take a look at NaCl again. NaCl here is a lattice structure made out of Na plus ions and Cl minus ions. In the solid, before it's dropped into water, this NaCl here is non-conductive. Do I have charges? Yep. The ions are already there, the electrons have been transferred, but I don't have the mobility. It's not like one of these sodiums here can actually swim through the structure, right? It's stuck vibrating just in place like that. However, upon dropping in water, what ends up happening is, as we mentioned, the NaCl dissociates, it gets dissolved. Water comes in and separates Na plus from Cl minus. That's referred to as a dissociation. It breaks up, or referred to as an ionization, because now we're actually charged. Remember when we were naming ionic compounds, we had worked out the ratio so the charges would cancel. The formula unit in NaCl is just 1 to 1 there, but water would have come in and actually separated all the positives from negatives. Now in our mixture, we now have just dissociated Na plus ions and Cl minus ions. Do we have charges? Definitely. Can these charges here move? Definitely. So in that case here, it's going to be conductive. And in fact, they're actually qualifying here which one is actually the most conductive, meaning what we want is we want to have the most ions in solution. This one here could come to us in two different ways. It can come to us in terms of molarity. It could be something like, I have 1 molar NaCl and 2 molar MgCl2. Well, just the concentration itself, this solution here is more concentrated. That would end up, when I break up 2 molars worth of MgCl2, that's going to be way more ions than just 1 molar. Even if in this situation here, even if I did equimolar solutions, even if I played fair, if I made both of them 1 molar, we also need to worry about the mole ratio in the compound. MgCl2 actually breaks up to end up forming Mg plus 2 and 2 chlorides. So for every MgCl2 that breaks up, even if I have 1 molar, based on the mole ratio, 1 molar, I'm going to get 2 molar, I'm going to get 3 molars worth of ions, whereas in this case here, if it's 1 molar NaCl, I'm going to get 2 molars worth of ions. So the more ions we have in solution, whether it be the starting concentration is higher, whether it be because of mole ratio it's higher, both of those will be most conductive. So in that situation, I would say MgCl2 is most conductive here. This CH3COH here, it is an organic compound. This one here we're actually going to learn in our next chapter. This is actually referred to as a weak acid. So even though it looks like it has an OH here, we'll study this a little bit later on, the OH here doesn't sort of let go of the carbon all that easily. When you drop this in water, water is just able to separate off this H. Because I'm able to release an H+, that makes me an acid, but my bonds are actually so strong, I don't break off the H+ really, really easily. So even if I had a really high concentration of this one here, we'll see more so in the next chapter, the equilibrium constant is very low, the reactants are actually favored, so the amount of ions that we get from something that's weak is very low. They can't compete with typical salt here in breaking up. Right? So that just highlights for you some of the vocabulary that we saw here. When we start looking more so at dissociation reactions, remember when you're breaking things up, don't break it up into too much. So let's say I take ammonium sulfate, and let's dissolve this one here. Hey, it's an ammonium compound, so I know it's fully soluble. So as it breaks up here, it's going to follow the mole ratios. We're going to get 2 parts ammonium and 1 part sulfate. The polyatomic internally is actually covalently bonded, but we're looking at the ionic bond between the positive ammonium and the sulfate. Water is just going to separate ammonium from sulfate. So typically when you dissociate things, you're going to still have one group that's positive, one group that's negative. Don't be tempted to make it, oh, it's N-3 and H plus 1. And it's just the polyatomics are actually just going to stick around. Okay. As we start looking at the solubility, so we're going to now focus in, let's imagine we already have a saturated solution. The solubility, let's imagine, let's consider a saturated solution of PbI2. Okay, just one random compound here. Remember, there's actually 2 different ways of actually making this PBI2. So it's important to note which one it is. 2 ways to make the solution. And the setup was different depending which way it was. The easier way was, let's pretend we had started off with a solid, so I just found a bottle of lead-2 iodide, and I just start dissolving the solid. I have some amount of water here, I have my PBI2, right now it's in the solid form because it's out of solution. Ionic compounds are typically solid, and what you do here is you slowly drop it in. You drop it in here, you might manage to get a smidgen to actually dissolve, whether it's soluble or low soluble here, but eventually, because I want to be saturated, I want to have hit equilibrium, I want there to be a precipitate. I want there to be some excess left over, so that I wait long enough here that there is a rate of dissolving equals to the rate of recrystallization. In that case there, I would write out the two equations. I would write out PBI2, that's your solid. Remember, we had put solids on the left-hand side, so that way your KSP expressions would end up looking nicely. To iodide here, aqueous and aqueous. Aqueous stands for dissolved in water. In this case here, the word solubility always describes the solid. It always describes how much of this compound will actually break up. Because I am actually starting off with PBI2, let's call it X, we will definitely follow the mole ratio, right? The only reason why there would be lead in solution and iodine in solution is because of the solid, because of the ratio here as it breaks up. X amount that breaks up PBI2, it's going to make PB2 plus as X, twice I minus, so it's going to be 2X. So in this case here, when you dissolve a solid, because we depend on the reaction, it's definitely going to follow the mole ratio. That's what I would say is the easier way of making a solution because it follows the mole ratio. If we're not told and we're allowed to assume, I would assume this way because I can actually make predictions on what ions I get. For all these problems here, I'd always start off, once you recognize what the salt potentially could be, you do want to write out this equilibrium expression, also write out the KSP expression. Remember KSP at the end of the day, KSP is KEQ. Right? It is that equilibrium constant, it's products over reactants, it has no units, it only changes with temperature, all that is still true, but we're calling it this time a solubility product constant because what ends up happening is, because the solid is on the left side, we're going to have the expression be just the product between the two ions. The numbers still go up in the powers, the solid is always ignored, so I don't need to bother with the divide by 1. And KSP, we saw some questions towards the end of our chapter here. KSP becomes some sort of magic value. If your concentrations are high enough, when you multiply them through, as you hit KSP, KSP became a test for when the solution became saturated. More on that in a second. So we have those two solutions here. In general, when we have any placeholders, whether we have the numbers or whether we have just X's as placeholders here, I would just punch them directly into this expression here. Although there is a correlation here, if something here is very soluble, if something here dissolves very well, that's going to generate a lot of ions. If I have a lot of ions, my ion concentration will be really high. If I have relatively big numbers and I square them and multiply them here, I get a relatively high KSP. So just as a general conclusion, a more soluble salt, I'm just going to say usually, has a bigger KSP. Right? So those are proportional. The smaller the KSP, typically less soluble it is. On our KSP table here, we see all of our KSPs are like 10 to the negative 5, 10 to the negative 9. They're all tiny, but which ones are relatively big still indicate which ones are actually going to be more soluble. Okay. I want to emphasize in this case here, although they are correlated, when one gets big, the other gets big here, they are two different numbers. Solubility, in this case here, is expressed in moles per liter. It describes how much will actually dissolve, whereas KSP is a constant, no units here. It comes out of having multiplied your ions here. All right. Let me make one other note here. Solubility. So I mentioned solubility usually goes underneath the solid. Solubility could be described in terms of grams per liter. So whether it is, I have a 500 ml solution and I managed to dissolve 2 grams before this thing here starts precipitating, I imagine that's sort of the maximum amount there. Because I do want to use the mole ratio, I can't use gram per liter. I need to calculate over for something called molar solubility, which is basically re-expressing this number, but instead using moles per liter instead. So if you look at your unit conversions here, if I want to get gram per liter over to mole per liter, the conversion factor that I need, grams on bottom, moles on top, I would actually need the molar mass on the periodic table. So throughout this chapter, anytime they throw out to, how many grams of this compound would I need here, you can think, okay, we need to have molar mass for this part. All right? Let me give you one practice question for this one. I want you to calculate for me, find how many grams of Ag2CrO4 can be dissolved into 500 milliliter solution. Okay? So if you can, I would start off with a picture. Right? We have a 500 ml container. I know I'm going to end up being divided by liters, so I'm just going to convert that here. Okay, so this is 0.500 liters right now. Right now, the concentration of AgCrO4 is absolutely nothing. The AgCrO4 is a solid, and I'm going to start dissolving it into this 0.5 liters. Every salt would dissolve to some extent, but if you check your KSP table, the KSP for this compound is actually given to us as 1.1 times 10 to the negative 12. We actually utilize this compound. This compound actually appears red for our chloride titrations. Basically, when I run out of chloride in my reaction, the silver can only react with the chromate indicator. When it turns red, I know when to stop. In this case here, I want to figure out how many grams can I actually dissolve in. Again, they made this mention here grams. I'm thinking I'm going to need molar mass for this compound here. When you know what the precipitate potentially is, I want you to write out those two expressions. I don't care what they're asking you. Ag2CrO4, the equilibrium reaction will form 2 silver and 1 chromate. And I'm going to have the KSP. This one here is equal to the silver concentration squared and the chromate concentration here. Regardless of the question, I had to write out those two things here. This time, what they have given me on the table, 1.1 times 10 to the negative 12, I've given this constant here. When you multiply this in this fashion, it gives you this number. Again, note that this number here is very tiny. So this one here implies reactants are favored. I have more reactants at equilibrium. It's a little bit harder to appreciate in this case here because the reactant itself is actually a solid. That's why it was a divide by 1 here. Remember, there's one way that follows mole ratio, dissolving a solid. That's what is implied as in this case here. I'm dissolving solid. So let's put in an X for the molar solubility. The solubility is a number that always describes a solid. If I know that's X, I can follow the mole ratio. I'm going to get 2X, I'm going to get X of this. And like I mentioned, whenever we have these two numbers, I can punch them directly into the KSP expression. So 2x all squared times x. This becomes a 4x squared times x. So we have a 4x cubed is equal to this 1.1 number. 1.1 times 10 to the negative 12. I would need to divide by 4 and then do the cube root. 1.1 e negative 12 divide 4 with the cube root. This one here gives me 6.5 times 10 to the negative 5. Always when you do these questions here and you solve for x, go back and reread the question. I've only found x. X is great. It's the solubility. It describes how much of this would dissolve. I have not, at this point here, used the volume yet, and I have not actually calculated over to grams. Again, there's that hint of grams. Okay, maybe we need to use molar mass. So let's just go over here. Let's find out how many grams of this compound can actually dissolve. Now we're going to use our volume. The liters of solution that I actually have is 0.5. The molar solubility was the 6.5 number. That's how much of the silver chromate would actually dissolve, moles per liter. And then again, when we need to get to grams, we need to use the molar mass of silver chromate. So we'll just add up here. Silver is 107.9. I'm going to times 2 for them, plus chromate, 50 plus 52, plus 4 times 16 for oxygen. I get a molar mass of 331.8, and that's how you get it over to grams. They can word this question in a slightly different fashion, so 0.011 is our answer. They can word it as, oh, I took a saturated solution that used to be 0.5 liters, I evaporated off all the water, and I got 0.01 grams when it was dry. Basically, they're just emphasizing the amount of material in that solution is this grams. I divide it by liter to get the solubility. I use the molar mass to get the molar solubility, and I can do this other work to find KSP if I didn't have it. Alright, so that's the one way of making a solution, dissolving a solid. The other main way of making a solution is, what if we ended up mixing solutions? What if we ended up just tossing two different materials together? So let's make the same sort of lead iodide solution, but this time, maybe my solution is actually PbNO3 Again, you might be like, oh, where did the nitrate come from? Remember, I just memorized nitrates are always soluble. You're never going to have a bottle of just pure lead ion. It has to be counterbalanced by some negative. In this case here, the lead nitrate will dissociate to produce the lead ion that I want. The nitrate is just going to sit around as a spectator, no problem. I'm going to pour this lead nitrate solution. Let's toss it in with another solution of potassium iodide. Right? Potassium iodide, again, where did the potassium come from? Well, potassium is an alkali salt. That guarantees it's going to be fully soluble. This is going to generate, some K plus in solution and some iodide. I just care about the iodide. And I just want to emphasize in this picture here, you'll notice the lead is coming from one side, the iodide is coming from something totally different. We didn't start off with a solid. There's no reason to actually follow the mole ratio. There's one added thing here. Because we're mixing two solutions together, both solutions get diluted. So I want you to do a C1V1 equals C2V2 for the lead nitrate. I want you to do a C1V1 C2V2 for the potassium iodide. That's just true because the total volume is now bigger. The total volume, right, just V1 plus V2, is actually going to be the V2 in these calculations. Figure out what the concentrations have dropped to now that the pool is bigger. And once you find the concentration, it's the left-hand side that will generate the lead ions for you. It's the right-hand side that's going to generate the iodide ions. Again, regardless of the question, I still want you to write out the two equations. Put the solid on the left side. If I potentially end up forming a solid, technically it's a product of my reactant. It's a product of my reaction, but I'm going to still show the solid on the left-hand side so that my KSP expression remains consistent. So even though this PBI2 was it was created upon this mixture here, when I write out the dissociation equilibrium expression here, I still always have the solid on the left side, so that's why the KSP here would just be the concentration of ions multiplied. Right? This time, because the lead came from its own solution, I'm giving you the lead. Just write that number here. We had calculated the iodide. I'm giving you the iodide. Don't worry about this 2 here. It didn't follow the mole ratio anyways. That 2 here was only important if I actually dissolved the PBI2. So in this case here, you can make a note. These ones here will not follow the mole ratio. Not mole ratio. Unless you're really lucky and coincidentally you just mixed in the right amounts here. But whenever you have these two numbers here, you can plug them directly in here. Do we still need to square it? Yes. All right. Earlier, if we followed the mole ratio, I would have doubled it and then squared it. In this case here, at least for this dissociation point here, that part doesn't follow the mole ratio, but once you plug it in here, the KSP here does need that 2 in the expression, so it does end up becoming squared. That part remains true. How we solved this question here was we started doing like a TIP or a trial ion product. Basically, the notion is I know PBI2, I know this one here is probably not very soluble because if you check your solubility chart here, the lead combination with chloride says low solubility. You can actually check the KSP. The KSP on the table is given as, for this compound, 8.5 times 10 to the PBI2, 10 to the negative 9. Again, we see that this is a small number. That indicates to me this is low soluble, right? We started treating the KSP here as this sort of magic number. When the concentrations get to be high enough to actually hit this number, that's when you actually hit saturation. So it is possible that we actually started off with so little lead at the beginning, so little iodide, it got even smaller after you did the dilution. Perhaps my PB2 plus, I'm going to call this my TIP value, my trial value. Perhaps my PB2 plus in multiplying my iodide, perhaps this one here, just make up a number. Let's say it came out to be 1.0 times 10 to the negative 10. Okay, so I just tested my current values. I did the dilution, I did the mixing, I did this PB times iodide with the squared, and I ended up getting this. In this situation, since your TIP is actually less than the KSP, my ion concentrations actually aren't high enough to actually hit this KSP limit here. Our conclusion was we have actually no precipitate forms. The reason for that here is the TIP would need to get bigger, and then it would hit KSP. For the TIP to get bigger, TIP is the product of the ion concentrations. I need more ions, which means any extra solid that I toss in, it needs to break up. The precipitate won't be left over. What if your TIP value or your Q value? What if when I did the dilution here, I tried calculating this PB and I minus squared? What if my value was like 5.0 times 10 to the negative 8? So the amounts that I randomly added, they didn't follow the mole ratio, but I see that in this case, since my Q is actually bigger than KSP, my ion concentration currently is too high. Why could it have been so high? Well, the lead came from one totally separate solution. Iodide came from its own solution here. Right now, my ion concentrations are too high. What I need is the Q to end up dropping, to end up hitting KSP, For my Q value to get tinier, I need less and less ions. To get less ions, I need to shift over to the left side. Basically, it's going to end up precipitating, so definitely in precipitate forms. So that's how we can use KSP here. We even did some sort of maximum limit kind of questions here. We can say, if I know the lead concentration, what's the maximum of iodide I can have? Basically, the KSP limit is what I need for a precipitate to just form, for a precipitate to just happen. Now, notice in this question here, you can add a ton more solid, right? Even when a precipitate forms, like let's say I have a saturated solution, right? You can add a ton more solid, no problem. The amount of solid here may have increased, but because I may have hit the saturation point already, I'm not going to dissolve any more concentration into solution. The dissolving will still happen, recrystallization will still happen here, but the amount in solution is actually fixed based on the solubility. Right? So let me just give you a quick wording of that question there. I want you to calculate the maximum sodium iodide concentration that can dissolve into a 0.10 molar PbNO3 solution. Okay. So again, as always, I like starting off with a picture if I can. So we have our container. This one here is currently 0.10 molar PbNO3. PbNO3 is a nitrate salt, so I know it's fully soluble. So imagine this is our reactant. It's going to follow the mole ratio. I basically just care about the lead because the lead that's actually going to react with iodide. Ooh, big difference. I changed it. Instead of potassium iodide, it's sodium iodide. Still, I'm just focusing on the iodide here. I already have my lead concentration as 0.1. And now what I'm intending to do is I'm going to mix in extra NaI. That could be in the form of grams. That could be, in this case here, another solution. The solid that can potentially form, the precipitate that ends up, this one here would be PbI2 like we've been doing. So PbI2, Pb2 plus 2I minus, right out the KSP. I would give you marks just for writing these two expressions. Right? Because we are at equilibrium, our equilibrium constant expression is given by KSP. In this situation, because the I minus and the Pb2 plus came from two different mixtures, I already knew the lead is 0.10. But unfortunately, because I'm mixing solutions, I can't just follow mole ratio. Oh, if lead is 0.1, this one here has to be 0.2. I didn't start off with PbI2. In fact, the NaI is going to break up to end up forming Na plus and I minus in a 1-to-1 ratio. I want to know how much iodide, X, I don't really care about this 2 here, how much iodide can I toss in before we end up hitting this KSP limit, before we max out the solution. So we're going to take the KSP we had from earlier, either given in the question or you just look it up on the table. We had the number 8.5 times 10 to the negative 9. This has to equal to 0.10 multiplied by X, which is our iodide concentration. Our iodide would have come from sodium iodide. Still need to do the square though. 8.5 e negative 9 divide 0.1 with the root. This gives me an X value. X is equal to 2.9 times 10 to the negative 4. Always go back and reread the question. X was the placeholder for this is how much iodide I can drop in. I didn't care about this 2 here. I told you how much iodide I have. I didn't need to follow the mole ratio. This is actually the amount of maximum in this question here. It's the maximum iodide. Likewise, the NaI, this is 1-to-1 ratio. Maximum iodide in solution. Or you can frame this number here a different way here. You can say it's the minimum needed to saturate. All right. One last little note here. We have this equation. So I have PbI2 becomes Pb plus 2 and 2I minus. In terms of this compound here, the solubility, like I mentioned, means how much it dissolves. What if I want to increase the solubility? What if I want to make this solid here get to dissolve better? Basically, you just need to deal with a little bit of Le Chatelier. Do I want to shift left or shift right for that to happen? Solubility describes the dissolving reaction, how much of this breaks up. Increasing solubility would imply I end up shifting to the right. Of course, you can use temperature here, but because we want to deal more with common ion effect, what we're going to do for this case here is we're going to add a salt to precipitate out either the Pb ions or the I minus ions. Basically, I'm going to force the lead. Let's throw in something totally random here. Lead chloride is also low soluble. So let's add in NaCl. Well, why NaCl? Well, NaCl here will become Na plus and Cl minus. When lead is in the presence of chloride, that's actually going to solidify out to become PbCl2 solid. So you can imagine having your beaker. We already had lead iodide, PbI2. We already had our maximum Pb solution and iodide solution here. Now you come along and you add NaCl. The Na is just going to be here. I don't really care about it. But the Cl minus is going to start tapering off some of the solid as PbCl2. In that case there, as it pertains to our initial equilibrium, the lead concentration goes down. It shifts the whole equilibrium to the right. So that increases solubility. The one that doesn't work is you can't add any more PbI2. I'm going to make a note here. If you try to add PbI2, remember this one here is a solid, you may end up with more PbI2 in solution. There's no doubt about that. But because this is a solid, this one here does not shift the equilibrium. Does not shift the equilibrium. So no change from adding the solid that is already participating in the equation. Flip it around here, see if you can get the logic down. How do we decrease solubility? Well, if I want to sort of prevent the dissolving reaction to happen, I want this equilibrium to actually shift left. Both of these are examples of what's called the common ion effect. I'm dealing with the ions that are in solution. Either I'm trying to pull the ions out to shift the equilibrium to the right, or I'm going to add some salt. Pretty much, I just want to add lead ion, I want to add iodide ion, but I'm never going to have a bottle of just pure lead 2 plus, pure iodide minus. Add salt that contains these solutions. So it could be PbNO3 or I minus. It doesn't matter which one, such that if I increase any of these ones here, it shifts the equilibrium to the left, and therefore it makes it harder for the solid to actually break up. Okay, so keep practicing through your questions. Just let me know if you have any problems. Thanks, guys.